Hello everyone, and welcome back to a new episode of Silicon Zeros. As I mentioned in, I think, the previous episode, I am just about out of time to record things in the near future, so I'm going to declare that this is the last episode of the series. Now, maybe in a couple weeks I'll come back and record, and you guys, will look and see, gosh, there's more episodes, even though he declared the end, and that'll be nice, but no promises. I think I probably won't. At any rate, I'm going to be done playing for a couple of weeks now. I hope that you guys have enjoyed this series, and hopefully also enjoyed the game. I'm glad I got the early access, and I've had a lot of fun recording this. I always enjoy programming puzzle games as long as they're reasonably well put together, and this is. So, what are we doing in this last episode? Well, I have made a few small improvements to a lot of puzzles, so we'll go look at some of those briefly. And then I also solved Divide. So I think that we will finish with an explanation of what that is all about as sort of a climax, since we're not getting to the really, really hard puzzles like these two. And who knows about finale. Probably it's a CPU that does both of these things, but what do I know, right? Okay, great, we're doing that. Did I improve anything over here in the twos section? I still don't have a perfect implementation of multiply, and I still don't have a perfect implementation of alternator, which makes me feel silly. Flip? No, I think all this stuff I already had. Okay, so everything that I've done has been in the threes, basically, and also some in the fours. The first one is Combiner. I think I was using like 60 milliticks or 50 something, and the ideal was 48. So I sat down to see what's going on with that. Remember, Combiner is one that just says, read slot 0 and slot 1, add them together, and put it in 2. And I think I had been using, like... I wish I had saved the old, the old solutions. It's a little bit hard to do that. But the new solution makes use of this sort of register bypass thing. I think that what I was doing is I was doing this in a single pipeline, maybe? Single stage pipeline? Because, like, right now I'm doing it in 3 16s, and I remember before I was doing it in like 2 25s or something like that. Which I think means that these 2 12s were like in the same cycle somehow or other. But so now the idea is just we start reading. By the way, something cute is if you're only ever going to need to read 2 inputs, you don't need an adder. You can just wire the 1 up to the latch. Now, this is cute, but didn't actually save me any modules, because now I need a 2. Before, I had an adder here, and I was reading 0 and then 1 from here, and then grabbing the 2 off of this adder and sending it here. But this way looks a little bit cuter, right? A little bit sneakier. A latch with just, it has 1 input on clock cycle 1, and then a different input the whole rest of the thing. Anyway, I thought that was cute. So we read in value 0 and send it to here, and then we read in value 1 and send it to here again. Meanwhile, value 0 has propagated this way. Now we've got the 2 numbers, we add them together, and we dump them into memory slot 2. So, nice and straightforward. But slightly faster than my old approach, which used, I think, a few more milliticks, and also maybe 1 more module? I don't remember. That was Combiner. Swap is one that I'm pleased with having improved. It took me way longer than I'm really happy with. Maybe this is the one that I was using 2 25s for. Yeah, because I was off by 50. I did it in exactly 50 milliticks, but you can do it in 45. I did it in 2 25s, now we can actually do it in 3 15s. So the idea is, here we've got this latch again, and now it's actually saving us time, because you don't need the adder, because we never need the 2 at all. But we're just supposed to write the output from 0 into 1 and 1 into 0. And I had a lot of trouble synchronizing these up so that we get the right values in the right place, and we don't get any, like... I kept finding, like, oh, of course! Why am I sending this value number 1? Like, this guy receives 1 eventually, right? And he writes the first input when he gets it. And I'm like, oh, well, the 1's already there. Why don't I just take the value straight off the reader instead of passing it through this register for no reason, is what I asked myself. But there are sort of two reasons for that. One is that then it means the writer and the reader are in the same phase of the pipeline, and so we end up with a cost of 25, so that sucks. The other is that then it's sort of hard to avoid writing too many times to here, like writing what we get out of memory slot 0 and then again out of memory slot 1. So it's easier to just we read the first value and we put it here, and then we let that stall for a cycle, saving it here, and finally send it this way. So right, we read value 0, wait a turn, 2 turns really. 1 turn just to get it into a register so we have a shorter pipeline, and then 1 extra turn to give us time to read the other value. And then we write that to slot 1. Meanwhile, this guy's input is... there's no 0 available for him to grab at the time when it's supposed to be writing, so I take the memory address we're reading from and give it the same treatment of cycling it through here. And then we read the value that was just put into this register as opposed to the one that was put in there a turn ago. So in the end, it looks like this. We've read 0 and 37, and they go here. And then they also get copied into these offset ones while we write a 1 and a 43 in. And then one more cycle later, these have actually been stored and the writers are trying to write them. It was just like, I couldn't figure out how to time things and like how much do I have to delay this? And what I eventually realized is, well, why don't I just make a register that's got like 8 things and put everything I could imagine in here, and then in the tester advance to tick 44 and see where the values I want are and just wire them up to where I want them to go, rather than trying to predict it all ahead of time. I have a simulator, right? So that was better. So great, we did this one. Advance. Yeah, hurrah. And so this is better than the best. I'm not sure if that's because I'm using this register as a self-delay instead of using 2 registers, or if like it's this innovation with the latch that has saved me a module. Don't know, doesn't really matter. It's kind of nice. So the last optimizations that I can remember doing, and therefore the last ones we'll cover in this puzzle, are in the 4s. Remember we started with all these parallel modules, where you have 2 completely independent CPUs solving offset, like we have 2 CPUs and we solve the instruction in memory set 1 and the one in memory set 0 at the same time. And then likewise for 2 and 3 and for 4 and 5 and so on. And so I figured out a way to shave 1 instruction off of each of these. Not 1 instruction, 1 module. And where did it go? Let's see. The problem was, or what I've figured out to remove was the clock cycle. If you've seen this, if you go back to when we solved this, and I don't know what episode that was, there was a 2 up here before, right? Because we're advancing our clock by 2 every cycle, so that we can in each cycle do 2 instructions, right? Makes sense. And indeed, you kind of have to do that, and so I'm showing you that after 1 tick, we're getting ready to write a 2 into the latch. But we don't need a number 2 to do it. We have a 1 already, and we have the value that we're... wait, what is going on? Right. We could just try to add the value in clock to something, but that would have to be 2. And we don't have any convenient 2s lying around, except for this one, which is the result we're aiming for. But what we do have is, we have clock plus 1 just lying around right here, right? And we need an adder anyway, so this one isn't costing us anything. We have a 1 lying around, this isn't costing us anything. So we can basically compute, instead of clock plus 2 and clock plus 1, we can compute clock plus 1 and clock plus 1 plus 1, yielding clock plus 2. And so this simple improvement is available in all 3 of those parallel solutions. Parallel puzzles, I suppose I should say. Hello? Why no go? There we go. So that was a nice improvement, and Pleasing Fungus will be decreasing the ideal for these for sure. He said that he probably will not be decreasing the ideal for puzzles like I think swap is an example where like the way to get the ideal is to wire a register up to itself. He thinks that's lacking in elegance, and if a player gets this and they're below the ideal, you know, great for them. But he wants the ideal that players see to be the one that is with somewhat elegant solutions. And then players can just sort of feel smart for beating it. Okay, so those are all the improvements I believe I have made. Or anyway, I have certainly made those improvements, and I believe that is all of them since the last recording. And now, to the finale, Divide. So I'll open this up and you guys can sort of look at it while I talk. One reason that one reason I put off Divide, you may recall, is that there were originally there was a specification that if you get a 0, as divide by 0, you should output 0. And I said, that's dumb, that's not how division works, you shouldn't make people solve that. And so he changed it, and now you don't get any zeros, so that's great. And by the way, you may notice we're 5 below the ideal here, but he showed me his ideal solution, and there are exactly 5 modules to cope with dividing by 0. So now that requirement is gone, 25 is the new ideal, and I don't count this one as beating his ideal. I just changed the definition of the problem, or asked him to, really, of course, and he didn't update his solution. So I think that if he had paid more attention, his ideal would be 25, and we would be right on the nose with it. So, the other reason is that I couldn't figure out how to frame division in terms of this game's language. Just like greater, usually in games like this, you get some sort of primitive like, by which I mean programming games. You get some sort of primitive like, is a thing greater than 0? Is it positive? Is it negative? You get something like that. And you can do that very quickly. And with that, the division algorithm that I've always implemented in programming puzzle games is like, take the dividend, subtract the divisor. Is the value negative? Well, actually, is the value still greater than 0? If so, keep going. Otherwise, you're done, right? That's the basic algorithm. But here, when it's tremendously expensive to do a greater than test, that doesn't seem like the right approach, and I couldn't figure out what the right one was for some time. But my solution to greater actually made me realize, thinking some more about that, I realized I could apply a similar sort of technique here, where I only ever count by 1. So the idea that I then had was, and we'll get to how these pieces represent this solution, was we want to start counting something either down from dividend towards 0, or up from 0 towards dividend. And at each step, we will update something, and then when we get there, we'll be done. And the details of how to update it are a little bit like not so obvious, but that's the idea. And just like I did with multiply? No, not multiply. I think it was greater. It's a lot easier to count towards a value that you are holding constant than to read a value in and then count it down towards 0. Right, I think it was greater where we did that. Yeah, so we just have this diff, which is the how much we're going to try adding to see if we can get these things to be equal to each other. And in divide, we have more than one number's worth of state, but the most important, in a way, piece of state is up here, total, a number which starts at 0 and counts up until it reaches the dividend. While that's happening, every time we count up, we check and see, like, hey, are these equal? If so, then we've found the answer. But what is the answer? Well, that's what these other two latches are about. We have, these should be familiar to anyone who's ever implemented division, quotient and remainder. Basically, at every step, we add 1 to remainder, while also adding 1 to our total, which you can sort of think of as subtracting 1 from the dividend. It's just easier to implement it as adding from 0 in this game. If I were going to write this in a real language, this algorithm, I would start with, I would add 1 to remainder while I subtract 1 from total, which keeps the nice invariant that the sum of these is, like, sort of always correct. Not that the sum of these two is always equal to dividend, but, like, that if you multiply the divisor by the quotient and add the remainder, you always get the total, or the dividend. And we would be decreasing the dividend in each step to preserve that invariant. Here, we can't conveniently preserve that invariant, but it's the same principle, is how we're updating quotient and remainder. So that if you did multiply them together, let's see, multiply quotient by divisor, add remainder, and subtract total, you get dividend. That's sort of the invariant we're keeping at each step of this loop. It's true when all of these are 0, and then it's eventually true when this is equal to dividend and we have the answer in quotient and remainder. But the details... Right, so that's what we're doing is quotient and remainder. How do we do it? We add 1 to remainder, and check, hey, is the remainder equal to the divisor? We shouldn't, if we're dividing by 5, we should never have a remainder of 5, right? So that means, oh, we found, we were dividing 43 by 5. We found that it goes into it at least once, right? Because we got a 5 in our remainder. Therefore, we add 1 in that case. So if this is equal, we use this selector to say add 1, or set quotient to the value of quotient plus 1. And this one we'll get to in a minute. It's just going to pass it through, though, in that case. And also, if this is 0, then we will reset the remainder to be exactly 1. Now, I had an earlier version of this puzzle where I reset the remainder to 0 at this stage and didn't add 1 to total. And this is just as correct, but actually more complicated and slower. It's simpler to reset the remainder to 1 and continue adding to total. So that's what happens when remainder equals dividend. That's the first sort of breaking point in our divisor. That's the first sort of breaking point in our loop. So we go through counting remainder up till it gets to dividend, and then resetting it to 0 and increasing quotient, while we're adding 1 to total, until we hit the special end condition that total is now equal to dividend, which means that the quotient and remainder that we have at this very moment are the correct ones, and we should output them. So that's what this comparator is saying. It's saying we have found the answer. And notice it's wired up to these 3 input selectors. So if we have found the answer, then we should reset ourselves and get ready for the next input. So this 0 is wired up to a lot of things, right? It's wired up to this, saying, hey, please use input 1. Instead of adding 1 to total, reset total to 0. It's wired up to here, saying, instead of, either adding 1 to quotient or leaving it alone, please reset it to 0. So total and quotient both get reset to 0. And in fact, so does remainder. When this hits 0, all 3 of these use the bottom path of their main selector and get reset to 0. And 2 other interesting things happen. One is the output of this becomes a 1 and is fed into the adder here, allowing clock to advance, so we can start looking at the next instruction. And the other thing that's kind of, I think, cute is it goes into this output selector. Which... Is there some way I could do without this? No, there's not. Okay, good to... Wait. Why not? Why can't I just always do this? There's got to be some reason, right? So, okay, let me explain what this is for, and then we'll think some more about whether we actually need it. The idea is that the destination is... yeah, I think actually we could just throw this away. My thinking was that the destination, we need to be careful not to write to these things until we have the correct answer. That's... No? I keep worrying that, oh, once we've reset all of these things to 0, we would overwrite the values in there, right? The values that we just wrote. But we wouldn't, because we would have a new a destination address to write to. We'll have read in a new instruction by that time. So I think I could take this out. But let's leave it in for the moment so I can show you the whole thing working, and then we'll try taking it out. So that's the idea. Just, if it's a 0, meaning we're not done, then don't pass the... Wait, what? Wait, in both cases it goes somewhere, right? When they are equal. Oh, I see. This one doesn't actually go anywhere. It looks like it does because of this wire here. Let me move it. So, actually both of these wires are coming out of the bottom one. So if it's 0, then don't send the address to write anywhere. If it's 1, then send the address to write here, and 1 plus the address to write here. And so that's sort of the basic thing, with one slight, ever so slight last wrinkle, which is a thing that I got wrong in an earlier version of this algorithm that I thought was correct but wasn't, is that we're adding 1 to total and adding 1 to remainder at the same time. And we're only checking, so far, total. So when we see, aha, total is equal to dividend, we can stop. That's great, but we haven't yet... Wait a minute. We haven't yet reset remainder and quotient. So you get the situation where you take, like, 10 divided by 2 is 4 remainder 2, is what we get out of this. And so I have this comparator here to say, wait a minute, are they equal? If so, like, do something smart. But do I actually need this? Add, because it seems like this value that I'm computing here for what to write as the updated quotient is exactly the same as what we would have stored in the updated quotient here, right? Or here, one of these, somewhere in here, is when we update quotient. This value plus 1. Yeah, so I think if we took the output of these two here, what we would ordinarily reset quotient and remainder to, we wouldn't need this adder or this selector, I think. Anyway, and so this selector is just saying to use either 0 if if remainder wasn't equal to it was equal to dividend, or the previous value of remainder if they were different. So let's run this through again real quick. just so I can... Oh, it takes forever, by the way, because we're counting up to 43 by ones, and then we count up to 63 by ones. It doesn't matter how big the quotient is. Our runtime is dominated by the size of the input. Whereas in a normal, like, if you have access to greater in a... If you have access to, like, greater than 0 in a programming puzzle game, you usually have a runtime that is dictated by how large the quotient is, rather than how large the dividend is. So, okay, but we don't actually have to wait. We can just do this and jump to the end, right? And we'll read this stuff in a minute. But now I want to try some improvements that I just thought of while I was talking about this. First is, what if we could just get rid of this? Right? And send value that was going here to here and here. Is it still correct? We'll write a bunch of garbage, but that's fine. Who cares? And then we'll advance the place we're writing to just as we no longer have the right values in scope. So let's try that. And we'll count up to tick like 41? Yeah, 41 will be an interesting one, probably. As you can see, we're writing stupid junk values into 42 and 43. But they're starting to approximate the right values. And if we just do a tick all the way up to 43, we're now writing the correct thing, which is that 43 is equal to 8 times 5 plus 3. And now, bloop, we've written them, and we move on to a new address. So in fact, I didn't need that at all. That's one module I've saved. Great. We'll just zip that to the end so I have the final answer. And remember, 5 of these things in the ideal don't really count. So we just improved from the what I think actually should count as the ideal of 25 down to 24. So we are still beating Pleasing Fungus here. That's good. But as I said, I think I can do more. Let's go look at test 3, which is the first one that has an even division. And I want to test this. Let's skip ahead to tick 24, please. And I want to look at some values. Okay. So here, we've computed that that the remainder was equal to divisor, and therefore we should use a 0 instead of Hang on, where is this going? Oh, this is the one that checks for dividend, right? No. This is the one that looks at divisor. Divisor is equal to remainder, and it sends a 0. Oh, it's sending a 0 to both of them, and I can't see it because of the dang tooltip. Right? If I zoom in, does that help? Yes, okay. So we're sending a 0 to here, saying to... oh wait, no. We're seeing that they're different. Oh, I skipped ahead a tick accidentally. Here we go. We're now sending a 1 to add to quotient and say, hey, actually, since the remainder was equal to the divisor, the quotient should be 1 higher than it is. And we're sending a 1 to this guy saying, actually, don't use the remainder, use a 0. So I want to see, are there some 12s and 0s lying around? And I think that they should be around here, right? Ah. So, not quite, it turns out. But there is a 12. We can take this, which is what we would be setting the quotient to if we were to continue this algorithm. So I think this will always be the correct thing to write here. So let's just pull this out of the way for the moment and take this and send it here. Now, of course, we haven't removed any modules, but I believe we're proving that this one could be removed. Nope, test 1 is broken. Why? That'll be interesting. So at the end of 43, we're writing nothing. Oh, well, haha, very funny. Because at one point I realized, wait a minute, we don't ever actually use this value that we're writing. we don't need to write quotient to quotient. We can just write nothing to quotient, and quotient will stay the same, which is very clever, but actually ruins this little optimization I was making. So I can wire quotient back up to here, and then that should fix the problem. Yes. Now it's not flashing anymore, so we have solved it. But let's go look at 3, and I can show you how that's happening in the simple case. Okay, we're at 24. And this is outputting a 12, but so is this. We're saying, oh, if we were to continue, we would put a 12 into quotient. And then this says, aha, we're not continuing, so there, put a 0 in instead. But we can still piggyback off of this 12 and make that our output. Meanwhile, we can delete this. Great, so that's another module trimmed out. And this one is not so easy to get rid of, right? Because we don't reset the quotient to 0 when it rolls over. We reset it straight up to 1, skipping sort of the 0 step, so that, as I said, I had an earlier version that set it to 0 and it didn't advance total, but that proved to be slower and take more modules. It's simpler to just reset it to 1. Which means, sadly, that I don't think we have any convenient zeros lying around that are non-zero, that are... We don't have a convenient version of, like, what would we write to remainder? It's this, but it's never 0 is the problem. So we actually do have to say... based on this, either take a 0 or take what we already have in remainder. I think we need that, right? Yeah, there's not a lot I can do about that one. But okay. I'm pretty happy anyway with having found a way to remove 2 more modules from my solution. I feel like there are some of these puzzles that, like that last thing I removed, here, this adder, well, I'll leave it up here, but I feel like it would have, we're adding together this value and this value, right? And it turns out that I think we already have a really similar value, which is like here maybe? Adding together this value and 1. So it's not so obvious. I was thinking, wouldn't it be nice if the game told you, you know, you have 2 modules with the exact same inputs. Why don't you try removing one of them? I don't think it actually would have caught this, but I suspect there must be some problem of mine lying around that meets exactly those criteria, right? Completely pointless module that I just never noticed. But I guess a lot of such cases are subtle, like those 2 were only equivalent because these 2 were always 0 at the same time, or I don't know, something like that. And there's no way the game could be expected to tell me that. And it really, even if it could, it shouldn't, because that's part of the programming problem, not the problem of like recognizing what wires are on the screen, which I think belongs to the computer more than to me. Okay, well, so that was a pretty cool divide, I think. It's nice to have a programming puzzle game that I have to apply different algorithms to. Like, Shenzhen.io and TIS-100 also, like, were really different in the kinds of things you had to do, because they were all about logistics, almost. Not the algorithm, but just how do you get these stupid, tiny things with no space in them to talk to each other in the right order. And so that was different from a lot of programming puzzles. And this one was different. I'm not sure why exactly. I guess just we had like fewer primitives available, I guess. And those primitives were a bit weaker. Right? Like these Normally in programming puzzle games, you'll get like a multiplier, you'll get an or like you'll get an if or something. Like here, what we get is pretty flimsy, and you have to think about ways to solve these problems that are different from, like, okay, Human Resource Machine, right? I had fun with that game for sure, but the algorithms you use in there are pretty much the same ones as you would use like if you were writing assembly in a really bad language, right, on a really bad processor, or what you would do if you were implementing. If you were like, I want to understand how math works through programming, and I want to implement division in terms of subtraction, I want to implement multiplication in terms of addition, or whatever. It's basically just like the same algorithm. And it was fun to do in terms of the Human Resource Machine stuff, but it was nothing particularly new. And this, I feel like, gives you a weird set of tools that I don't think I've seen before. So anyway, I'll just say I enjoyed it, and I'm just having trouble wrapping up and ending this series, you know? I've been recording this for a while now, and it's going to be a shame to see it go. But I hope you guys have enjoyed it. I wish this game the best of luck on Steam. It's still, at the time of this recording, is not released. I'm doing all this long before the final release. Just sort of binged it over the course of like a little bit less than a week, I think. You may laugh because it's been like, I don't know, several months since the first episode, but I really have done this in just a week or so. It's been a lot of fun. So, I guess that means now I'm finally out of things to say, right? Okay, thanks for watching, and I'll see you in some other playlist.